Hello everyone, welcome to Basic Electronics Tutorials. In this video, I'm going to take up the first numerical on center tapped full wave rectifier. Let me read out the question first. In a full wave rectifier, the input is from a 30 volt transformer. The load and diode forward resistances are 100 ohm and 10 ohms respectively. Calculate the average output voltage, rectification efficiency, and percentage regulation. Well, if you look at the first sentence of the question, there is some confusion here because the question does not specify whether this is a bridge rectifier or a center tapped full wave rectifier. So how do you find out that? Look at the way in which the input voltage is specified across the transformer. It is given as 30 0 30. So we now understand that there are three terminals across the secondary. Among the three rectifier circuits we have, which are half wave rectifier, center tapped full wave rectifier and bridge rectifier, it is the center tapped full wave rectifier that has three terminals across the secondary, and particularly in the center tapped full wave rectifier, the second terminal is center tapped, that is, it is connected to ground. So the voltage specification what we are given here, which is 30 0 30, will suit the center tapped full wave rectifier. With that, we now understand that this is a numerical on center tapped full wave rectifier. Let us start with the solution part. Let me now write down why we have considered this to be a center tapped rectifier, and then I will move on to the solution part. Right, with that established, now we can start with the solution part. Let me start by first writing down what are the given values. We are given that the load resistance is 100 ohms and the forward resistance of the diode is given as 10 ohms. Since this is a center tapped full wave rectifier, the RMS value of the secondary across each half of the secondary is 30 volts each. Let me denote this voltage as VRMS, and this is equal to 30 volts. Let us now start finding the average output voltage. The equation for average output voltage is given by VDC is equals to IDC multiplied by RL. But please note, we are not given the value of IDC as well. So what I will do is I'll call it as equation 1, and now I'll move on to write the equation for IDC, which for a center tapped full wave rectifier is given by 2Im divided by pi. Let me call this as equation 2. Once again, in equation 2, we don't know what is the value of Im. So I'll write the equation for Im, which is the maximum value of the current across the transformer secondary, by using the equation Vm, which is the maximum voltage across the secondary of the transformer, divided by all of the resistances in the circuit, which is the diode forward resistance Rf plus the load resistance RL. Let me call this as equation 3. In equation 3, we don't know what is the value of Vm, so let me now write the equation for Vm, which is the maximum value of the secondary transformer voltage, and this is simply equal to root 2 multiplied by Vrms. Now we know the value of Vrms, which is 30 volt here, so let me now compute Vm very quickly. This is equal to root 2 multiplied by 30 volt, and this is equal to 42.4264 volts. Once we have found the value of Vm, now I can compute Im, which is equation 3. So I'll substitute for Vm into equation 3. I'll rewrite equation 3 once again here. I'll substitute the values. Vm we just computed is equal to 42.4264 The value of RF is 10, value of RL is 100. So the value of IM is equal to 0.3856 amperes. Once we find the value of IM, we can now find the value of IDC by substituting for IM into equation 2. Let me rewrite equation 2 once again here, which is equals to 2 divided by pi multiplied by the value of IM is 0.3856. This gives the answer for IDC as 0.2455 amperes. Lastly, I will now substitute for IDC into equation 1, which is for VDC. Let me write equation 1 once again here. IDC is 0.2455. RL is 100 ohm. So the value of VDC is 24.55 volts. This is the answer for the average output voltage. Let us now move on to the next part of the numerical, which is to find the rectification efficiency. It is denoted by eta and is given by eta equals PDC divided by PAC, where PDC is the DC output power and is given by PDC is equal to VDC into IDC. We have values for both VDC as well as IDC. Let me now substitute for them. PDC we calculated as 24.55 volts and IDC was 0.2455 amperes. So the output DC power is equal to 6.027 watts. Let me now compute PAC, which is the AC input power, and it is given by PAC is equal to Vrms multiplied by Irms. Please note both of them across the secondary of the transformer. We have not computed Vrms, so what I will do is I will substitute Vrms in terms of Irms, which can be done as Irms multiplied by the diode forward resistance Rf plus the load resistance RL. Then we have the Irms as it is. Simplifying this, we will obtain Irms square multiplied by Rf plus RL. Please note we have not computed Irms previously. So what I will do is I will write Irms in terms of the maximum current, which can be done as Im divided by root 2. Then we have a square. Following that we have Rf plus RL. Let me now substitute values for this. The value of Im is 0.3856 divided by root 2 whole square. Then we have Rf as 10 and RL as 100. This is equal to 0.0743 multiplied by 110. This gives us the answer as 8.1778 watts. This is the value for the AC input power. So, in the equation for rectification efficiency, which I'll call it as equation 4, we have found both the values of PDC and PAC. Let us now substitute for these into equation 4 and find the answer for rectification efficiency. Eta equals to PDC divided by PAC. PDC is 6.027, PAC is 8.1778. Therefore, the rectification efficiency will be 0.7369. In terms of percentage, it would be 73.69%. That is the answer for the second part of the numerical, which is to find the rectification efficiency. Coming back to the numerical, let us now lastly find the percentage regulation. The formula for percentage regulation is VDC under no load condition minus of VDC under full load condition divided by VDC under full load condition. Let us find VDC under no load condition and full load condition and come back and substitute the same in the equation here. I'll start by first finding VDC no load condition. Let me denote it by VNL. It stands for VDC no load. This is equal to 2 Vm divided by pi, where Vm is the secondary maximum voltage. We have previously computed this as 42.4264. So let us substitute that. So the answer for VDC under no load condition is 27.0094 volts. Let us now compute VDC full load. I'll denote it as VFL, standing for full load, equal to, this is IDC multiplied by RL. IDC value was 0.2455, RL value was 100 ohms. So VDC full load is equal to 24.55 volts. Let us now substitute all of them back into the equation for percentage regulation. This is V no load minus V full load divided by V full load. V no load is 27.0094, V full load is 24.55, and the denominator also is the same, and therefore the percentage regulation value is 0.10016. Please note, we have computed percentage regulation. So let me modify the formula by multiplying it with 100. That will give us the percentage value directly. So the percentage regulation is 10.016 percentage. This is the solution for this numerical. Well, with that we have come to the end of this numerical. If you like this video, kindly like and share this video and subscribe to my channel for more tutorials on basic electronics. Thank you for watching. Have a good day.